mouse over there. So all right, so let's get started, everyone. So great. So this is the third lecture on clustering. Mostly gonna be talking about a mixture of Gaussians. This will be one of these fun lectures where we put a whole bunch of stuff together. It'll actually be kind of, I think it'll be, you have all tools to do this. We'll just kind of see all this stuff kind of fit together in one lecture here. Look at, the schedule, so homework 4 is due today with the extension. Been getting a lot of great questions about this. It's exciting to see all of you guys putting this, these ideas together and solving everything. I feel much better about how well you're kind of, progressing on this assignment than I did a couple days ago. So that's good. I guess the other thing I didn't talk about on Tuesday was, we released the grades for quiz 5. The quiz 5 grades were a little bit lower than the past 3 quizzes, but I think on average over the last all the quizzes, the averages are like about where I want them. So I think it's okay. There were some fudge factors that we did in the grading. There's one question that was at least one a little bit harder than we had planned for it. So we tried to make up for that with some fudge factors. I suspect if you were to retake quiz 5 now after having done homework 4, you would probably do better. Is that kind of the impression? Yeah, sometimes the order of these things we change up a bit. You'll get to do better on the final exam. So that's good. Okay. But we didn't quite do as well, but I feel like after homework 4, you guys are gonna have a good understanding of this material. And I don't think it's too far off that I need to do any more adjustments on the grade. Okay, and then we will get homework 5 out by the first part of next week, and that'll be due kind of after the semester's over. All right, we have, and then there'll be one more quiz which will cover clustering and the core part of classification, and it won't cover the advanced stuff, which will be more of like a like a survey on the more advanced stuff in classification. Okay, let's try any questions on this. Great, so let's get into it with the lecture. Mixture of Gaussians. All right, this is going to be kind of a more advanced modeling of what does it mean to do clusters. There's a lot of different ways of interpreting this, and the mixture of Gaussians I like this way in that it puts a real kind of probabilistic modeling underneath what's going on here, in a way that it's otherwise going to be like k-means. It's going to be a lot like k-means, but it's giving it a proper modeling. This is a lot of other types of clustering don't have this type of modeling, and so it's kind of not as we ask, okay, what does this clustering actually mean? It's hard to answer that. In order to kind of do this, we're going to basically extend k-means and extend the Lloyd's algorithm for solving it. And to that, we're going to need to do 2 things. One is we're going to extend clustering to what's called soft clustering. And then the second one will be dealing with kind of kind of combining it with the ideas of dimensionality reduction from PCA. We don't actually reduce the dimension, but we're going to do some structure that's going to be similar there. Okay, and it's Okay, all right. So the first thing is so soft clustering. All right, so here we're thinking again, so input is just this, so point set and RD, right? And we're kind of measure this with some, so distance, we'll use just, so Euclidean distance. And what we're gonna do is we're gonna create clusters of these points, but we're not gonna assign a point exactly onto a cluster, okay? So each xi in X will have a so it's going to have a is going to have a partial assignment onto the cluster, onto so some cluster. Okay, it was before with the k-means clustering with so k-means, this was where we use this b of s function of x, and this mapped it to some cluster site sj. Okay, and with this site we said, okay, cluster x, this implied X is in this cluster Xj, which is going to be a subset of X. Okay, so that this was going to be a cluster. Okay, this is not what we're going to be doing now. We're going to be saying it's not, a point is not going to be exactly one cluster. It might be partially assigned to a few clusters. Okay, so let me draw an example here. Let's say this is S1, S2, S3. Okay, and we can draw like the Voronoi diagrams to understand the which so then if you have some data points here, you know which cluster they're in based on these Voronoi diagrams. And so the question is, what happens if you have a point right here, xi? Okay, xi is, okay, I'm gonna, by the hard clustering formulation, right, what I would do is I would do the, so the hard assignment of xi would be, it's exactly in this cluster S2, and that's where it is. But from a soft assignment perspective, say, well, it's pretty close to the boundary between S2 and S1. So I'm not sure, should it be in S2 or sorry, between S2 and S3. So it's not clear whether it should be in S2 or it should be in S3. So I might want to say, well, I'm going to partially assign it to S2 and partially assign it to S3. Okay, so what I would do is I would say there's going to be a weight vector. So for the soft version, there's going to be a weight vector. Okay, and this is going to be a vector, an element of what I call delta k, which is this is a subset of rk, so a k-dimensional vector, so that if I were to sum up j equals 1 to k of wij, this has to equal 1, and wij must be greater or equal to 0. Okay, so this is basically a probability. Okay, you see, I use this notation in a chapter in the book that we skipped, but like this is a notion of capturing a high dimensional probability. And what it would say is that, for instance, I could say Wi is going to be equal to 0.6.4. Okay, so this value is WI2. Okay, so this is the assignment probability onto cluster 2 is 0.6, and its probability of 0.4 onto S1. So that would be 0.6, and going this way, 0.4. It's closer to the site S2, so it's given a higher probability. It's next closest to site S3, so it's given a 40% probability, and it's pretty far from S1, so I can give it a 0 sort of probability. I don't think it's part of cluster S1. Okay, so that probability is going to be 0, and that's what the first term in this vector is. Okay. All right, so this kind of makes sense, sort of, so conceptually. I haven't said, okay, how would I? They're kind of okay. So there are kind of two questions that should probably arise if I'm using these weighted assignments. Okay, one is, how do I actually come up with these weights? Okay, and how do I use them inside of like an algorithm that's going to be solving for the cluster? Okay, so those are kind of the two questions we need to handle. And I'm going to give you a kind of one preview of how you might try and assign these weights. This is based on, and this is not what's used in mixture of Gaussians, but this will just be another way of thinking about this. This will be an idea from natural neighbor interpolation. I'll call this xi prime as another example. I'm going to assign the weights from xi prime onto the three clusters, and this is from natural neighbor interpolation, and this uses the Voronoi diagrams. I'm extending this. I'm going to say, what if xi prime was a site here? And then how would this change the Voronoi diagram? So what I would do is I would draw these new boundaries between these between xi and the sites, and xi prime would have its own would have its own cell in the Voronoi diagram. Okay, and then I look at the cell and I say, well, what fraction of the cell is in S2? What fraction of it is in the old Voronoi cell of S1? And what fraction of it is in the old Voronoi cell of S3? Okay, so I calculate these areas, and I divide the area by the total area of the cell, and so this leads to the weight, right? So I would say then that the weight of I prime 3 is going to be equal to, so let's just draw this by a picture, the area of the blue plus the area of the purple plus the area of the green. Okay, so I'm going to add up those areas and divide, I guess, divide the blue area by the sum of all of these areas, right? And so this is how I could assign the weight. Okay, so this is one way how to assign the weight. Okay, this is, and so in the soft clustering, so if we do a small example here, so soft clustering. So I could, again, let's draw a picture here with so 3 sites, S1, S2, S3, and I'm gonna draw some points here, not too many points, X1, X2, X3, say x4, x5, x6, and say maybe x7. Okay, so in the hard version of this, I would have points are going to be indexed 1, 2, 3, 4, 5, 6, 7. And the way I would think about this is that there are clusters 1, 2, and 3. Okay, and I'm basically going to assign them exactly to one cluster. So point 1 is going to have a 1 for point 1 and a 0 and a 0. Point 2 is going to have 1, 0, 0, 3, 1, 0, 0. 6, 4 is then going to be 0, 1, 0. 5 would be 0, 0, 1. 6 might be 1, 0, 0, and 7 might be, let's say, 0, 0, 1, right? It's assigned to maybe S3 here. Okay, for 7, I could store this more efficiently by just storing 1, 1, 1, 2, 3, 1, 2. So depending on how if you were to implement this, you could either store the assignment as this bit vector, and it's only one bit can be 1, the rest have to be zeros, or I can assign the index of the 1 bit. That might be a more efficient way. But what the soft assignment is going to do is it's going to extend the bit vector explanation, right? So now I have 1, 2, and 3. And so now point 1 might be, again, this might be 1, 0, 0. Point 2 now might be 0.9, 0.10, 3, 1, 0, 0. 4 might be 0, 1, 0, the same as before. 0, 0, 1. Point 6 might be 0.4, 0.3, 0.3. And point 7 might be 0.5, 0.5. Right? So I can think of storing these probabilities inside of some kind of k arrays here, if I have k of the clusters. So I'm going to conceptually be storing these more kind of complicated representations of the assignment. I still have a assignment, but it's soft. It's not like a hard clustering would be the top version. The soft clustering kind of gives some probability of this assignment. And this is helpful when things are kind of on the boundary and I don't know exactly where x7 is. I can say, well, let's split the difference. Okay. Okay, so this is, I have this other soft clustering is this other way of thinking about these problems. Okay, so this, hopefully this makes sense. This sets up this mixture of Gaussians. We're going to need, to do a mixture of Gaussians correctly, we're going to need to use soft clustering, and I will explain that why. But I wanted to introduce this first. Okay, so let's think of, let me get into mixture of so Gaussians, okay, and the input to this problem is x in RD, some endpoints, and it's going to be kind of some number of clusters k, okay, which is, I guess, greater or equal than 1. Okay, and so what I would like to do is take this data and fit k Gaussians to the data. Okay, so I can say that, so I can fit these a set of k Gaussians to say these k Gaussians, this mixture of these k Gaussians is what is representing this data. I want to find the best model of this. Okay, and so a Gaussian, if you remember, we talked about a normal distribution, which was kind of like this you had this mean and one standard deviation. This is a normal. A Gaussian is kind of a high dimensional version of the normal distribution. All right, so let me write down the PDF of a Gaussian, PDF of a Gaussian. We're going to write this as F. It's going to be parameterized by a mean. Okay, good. We know how to deal with means in clustering, and covariance. This is going to be the second thing that we're going to kind of changing from k-means clustering. We're going to have this covariance, which we're going to learn. And this will hopefully make more sense after thinking about PCA. And what we need to do is to define this likelihood function for a point x, this to be for some value inside of RD. Okay, and so this is going to look like the Gaussian representation. It's e to some power. I'm going to write this as exp. Okay, and this is minus 1/2 x minus mu. So mu is a vector. Okay, so now we need that this is a vector in RD. Then it's going to be a transpose sigma inverse, the inverse of sigma. Okay, so that means to multiply it by this needs to be in RD times D. It needs to be a square matrix that has to be invertible. Okay, it's to be in a D by D square matrix times x minus mu. Okay, so this is the core part of a Gaussian distribution. I left a blank here in front, and you might be wondering why I left the blank. The PDF needs to, if it's to be a PDF, I should integrate. If I integrate, it has to be equal to 1. So I need to put something in front so it's going to integrate to 1. And this is kind of is messy. 2 pi to the power d over 2. So it's 1 over that. And also, if I look at the covariance and I take the determinant of the covariance, I take the square root of that and I do 1 over that. Okay. The determinant of a matrix, this is kind of like a norm. It's something that as the matrix values get larger, the determinant gets larger. Hopefully you've seen the determinant in like a linear algebra class. If not, it's not so important. Okay, so this stuff is only here. So this, so if I integrate it, it's going to integrate to 1. It's going to turn out that we are never going to need to actually, so within the algorithm, we don't actually need to calculate this because we're going to use this, we're going to normalize stuff. So we're going to write out a sum of these things and then divide by them, and this part's going to cancel. Okay, this part will always cancel out. So we don't really, you don't really need to know what's in there. Just know there's technically a Gaussian has this normalizing factor, and we can pretty much just ignore it. Okay, so let's ignore that part in the blue circle there, and let's look at what is happening. Yeah, what's interesting is what's happening here. Okay, the minus 1/2, that's kind of like the normal distribution. Let's say what happened if if sigma is equal to the identity matrix. Yeah, that's ID, right? So this is the identity, okay? If this was the identity matrix, then let's look at this expression here. Then I can write x minus mu as sigma inverse x minus mu sigma transpose. okay? But the inverse of the identity matrix is just the identity matrix, and multiplying by the identity matrix does not do anything, right? So then this is equal to x minus mu transpose x minus mu, and this is just the dot product, right? So this is equal to x minus mu dot x minus mu. Oh wait, but if you take the dot product widths of something by itself, this is equal to the norm of x minus mu squared, the squared norm of it. Oh, okay. So now this is starting to look a little bit more familiar. Then this becomes minus 1/2 times the squared norm. Okay, so this should look like the normal distribution, right? The normal distribution, if you remember, this was basically e to the negative x minus mu squared divided by, so sigma squared. Right, so that was basically the normal distribution if you ignore this normalizing factor. And maybe that was just in 1D, so I don't need the norm. Those are just scalar values. But now with vector values, I have to think about with linear algebra. And this, okay, so what is this sigma inverse doing? Well, if let's say now if sigma is, if this is equal to, let's say, sigma squared times the identity. Okay, so that's equal to sigma squared, and zeros off here. Okay, then this expression, okay, this, I have a sigma inverse, so this is like dividing. And I can factor out the sigma squared, right? So this is going to be equal to 1 over sigma squared x minus mu x minus mu, which is equal to x minus mu squared divided by sigma squared. Okay, and again, this looks exactly like the normal distribution. Okay, but I'm not restricting that sigma is going to necessarily be this uppercase sigma is going to be a diagonal matrix. Okay, it could be anything. So how do I interpret it if it's not just a diagonal matrix? So one way would be if the diagonal elements, the sigma squared, are so like not all the same value, right? I can imagine different sigma squares, sigma 1 squared, sigma 2 squared, right? And what that's doing is I'm dividing different coordinates then of this higher dimensional space by different standard deviations, right? So if in general, if I have two, right, if I have a sigma 1 in this direction and sigma 2, what's going to say is that I'm going to be kind of stretching the space differently, right? So kind of like this, where there's like an ellipse, and I might stretch along one direction more than the other direction. The standard deviation is more along one direction than the other. Okay, that still has to be on the diagonal. If it's off diagonal, right, I might want to stretch it so it looks like this instead. Okay, well, what does this kind of remind you of? Yep. Yeah, so it should look kind of like the singular value decomposition. It's a square matrix though, and I'm actually multiplying it by something on both sides. So it's actually going to be like the eigendecomposition. Yeah, but as you know, these are roughly the same things. And this is kind of like a squared version of it. And I could decompose this into two matrices and do the singular value decomposition of, so both of these matrices. Okay, but there's something else going on here. I also have this mu. So if we're centering, if we're subtracting the center, which might be like the mean of the data, then this is looking like, so PCA as well, right? So I'm not just doing it at the origin, but I'm doing this kind of this stuff around mu, right? So I've fixed this point mu here, and it's the data with respect to the center. So if I just had x and x transpose sigma x, then I have to do it around the origin, but because I can subtract the mu, I'm doing this around this point mu. So there could be the original origin was down here, and there's this vector, this mu vector, which allowed me to shift it before I did this. Okay, so what does this look like with potentially with data? I could think of some data points here, and I would identify a mu. I'd identify this first kind of so the singular vector, say v1, v2, and then there's some scaling, sigma 1, sigma 2. Right, so I'm kind of fitting this data with this sort of with like an ellipse like this. But what I would like to actually do is not just do it with one, but gonna have all of this data is gonna kind of be in the same picture. Draw those, and okay, so what I'd like to do is this is going to be mu1. I'm going to have mu2, mu3, and a mu4. And around each of these, I'm going to draw some, think of fitting this with like an ellipse. Okay, so it could be circular, like with the second cluster. It could be kind of like oblong and stretched with these other clusters. There are some versions where you say, I don't want to deal with the covariance and the stretching, and I'm just going to assume the covariance is always the identity, and then you fit everything with the round version. But generally, with mixture of Gaussians, is thought of allowing this stretch factor as well. So I want to find a clustering that looks kind of like this, okay? And as we'll see, it's going to be, especially when you do this, it's going to be really useful to think of soft clustering, because if I'm in a location like this, if this is xi, well, this could be in U3 or in U4. And kind of distinguishing between those it's going to be hard. I could try and figure out it's more likely to be in U3 than U4, but it's kind of somewhat likely to be in both. And then actually to fit the right probability distributions for these, I need to factor its potential contributions to both, because x1 might be in one and say x2 might be in the other, but I don't know which is which. So I need to say, well, both could be from either of them, and in the limit, I need to kind of take their averages. Okay. Okay, great. So let's try and write down what we want to do so mathematically. Okay. So mixture of so Gaussians again. Okay, again, input x in RD and some k greater or equal than 1, and I want to and the goal is to fit k, so so to fit K Gaussians, okay, and this will give me a distribution. So I'd like to find so the output is going to be so a set of mu j sigma j, right? These are the parameters I need to describe the K Gaussians, right? For j equals 1 up to k, right? So these are the parameters, and I have an assignment. Okay, so a vector wi in this space for all xi and x. Okay, so for each data point, I'm going to have this soft assignment, this probability of assigning it to each of the the Gaussians. Okay, and so to calculate, and like how I could define, okay, implicitly map it to the closest point, I'm going to define okay, I'm going to define wij. Okay, this is the probability point xi is I say from Gaussian, the Gaussian mu j, so sigma j. Okay, and I want to get a probability, so I'm going to write down the likelihood mu j sigma j of xi and divide it by all of the likelihoods, j equals 1 to k of f mu j sigma j of xi. Okay, so this is the sum over all the likelihoods of all the assignments, and this is the one assigning onto the jth cluster. Okay, so by dividing through by all of these values, I'm going to ensure the likelihood is always going to be between 0 and 1, right? Just by definition of a likelihood function. And I'm dividing through by all the values I could possibly assign. So this will ensure that these values are all, the wij values are all greater than 1, or greater or equal than 1, and the sum of them over the values j is going to be exactly 1. So it'll ensure that it will fit into this pattern. That it's basically a probability of assignment. Okay. Okay, isn't the domain of the Gaussian unbounded though? Do you just pick points with a certain standard deviation? Yeah, so for every x, for any vector x I put into this function here, right? So I've got this important function here for the likelihood of the of this Gaussian. For any value x I put into here, the return value is going to be greater than 0. Sometimes people use a truncated Gaussian where you say, okay, if the value is less than 0, I'm going to round it down to 0. But for this, everything is going to have a value that's greater than 0, which turns out to be fine. That's not a problem. So we're going to have to choose these parameters, right? We have d parameters for the mean and d squared parameters for the standard deviation. So just like with k-means clustering, we had to solve for the centers. I could have picked any value for those centers. So if I pick the standard deviation to be too large, then yeah. So you're saying, okay, so if I pick the standard deviation to be large and I haven't worried about the normalizing, so what happens is if I stretch it out very far, then this term right here, this standard deviation is large, I'm dividing through by this, right? Because it has to integrate to 1. So then this becomes large, and I divide by a smaller number, and it's going to be a flatter, more so bump that's so spread out more. And so I need to by doing this, spreading out more, the total probability under that one is 1. So I don't get this advantage by making this standard deviation very large. So if I assign all the mixtures are equal weight, then I'm dividing through by all of the if you remember, there was some sort of coefficient, there was this blue circle thing that was in front here, but I can factor that out in front and it cancels, right? So if I fix those, so that those normalizing terms, so if I guess I do need to worry about them, because if the standard deviation becomes larger than 1, becomes larger in one than the other, it will actually, I'll have to pay attention to it here. So that's why this isn't a problem with this standard deviation. Yeah. Oh, the sigma and the summation terms look the same. Yep, okay. Let me do some stuff on the spot here. For the sigma, I will not put the little bars like this here. Okay, let me go back and fix that. In the okay, yeah, so these are, yeah, in LaTeX, these are slightly different. Oh, I did it again. So slightly different symbols. Okay. Okay, so in the book, there's slightly different symbols, so you should be able to tell them apart. But in my writing, I'll try and be careful. Yeah, okay, so this one, the first one is the sum. This is a sum, and this one is just the covariance of the Gaussian. Okay. Okay, great. So this is how we'll define these Wij. So once we've chosen the mu j's and the sigma j's, then the assignment weights can be given in this way. I calculate the likelihood of each one, and I say, the likelihood ratio of this distribution to the other ones is how I assign this weight. Okay, so then once I fix this assignment method, I can then write down an optimization. I want to find the arg max over the set of the mu j and sigma j. That is the sum, or is, I guess, the product over xi in x of the sum over the j equals 1 to k of the assignment of the ith thing onto the jth, so PDF, and mu j sigma j of xi, right? So I'd like to do the, this is the maximum likelihood. This is the joint likelihood over all of the data points, right? Based on the assignment to the, based on these, so Gaussians. I'd like to find the arg max of these. That's mu j sigma j star, and the set of these, there are k of these things I have to find, right? So this is what I would like to find. Okay, this is equal to the arg min mu j sigma j of instead of the product, I can do a log transform, right? So I can do the sum of xi into x, sum of j equals 1 onto k of wij log of this f. Okay, so I can do the negative of this. Okay, so I can do a log transform as well. Okay, this log transform, if I take the log of, again, if you take the log of this expression, right, and this blue part is going to factor out as a constant term, depending on sigma. Okay, so on uppercase sigma here, and then the log of the exponent is going to cancel, and I'm going to get and the negative sign is going to cancel inside there, and I'm going to get basically the sum of the squared distances scaled by sigma. Okay, so if I take the negative log of, let's say, of z, that's going to depend on sigma j times x mu, or x minus mu mu j sigma j minus 1. This is transpose x minus mu j this, and this is, say, the natural log. Okay, then this is going to be equal to x minus, yeah, we'll do x minus mu j transpose sigma j inverse x minus mu j plus some natural log of z sigma j. Okay, and okay, and remember, this term looks like x minus mu j squared with some special norm that depends on this sort of covariance. It's going to look kind of like a distance after some scale. Okay, plus some terms. So this is looking a lot like, if I want to minimize the sum of these, this look a lot like k-means clustering. If I fix the sigma j's to all be identity, then I'm basically recovering a version of k-means clustering with the like the soft assignment. Okay, so if I fix the sigma j to be the identity, then I get k-means with a soft assignment. Okay. So I'm going to have a different distance here, which that's okay. I can calculate it if I know the sigma j's. And the soft assignment, I know how to do the soft assignment. I'll always define them in this way. So it looks a lot like k-means, and it looks like something I can pretty much, so that we can do here. Okay, so let's take a little bit of break, and when we come back, I'll put this together. I'll write down the algorithm, and then we'll see. It looks a lot like Lloyd's algorithm, but we just have to be more careful in dealing with the soft assignment. And then we have to, the other step we have to do is to find the optimal mu and sigma, the mean and covariance, to fit the Gaussian given some data. So we have to do those two steps. But it turns out those steps will both be easy. Okay, so we'll take a little break here. Oh, well, we're trying to optimize. What does arg max mean? Yeah, so the arg max here, right? So if I want to find the right? So if I have a set and I want to find the maximum from that set, then I return the element of the set which maximizes, right? If I want to find, if I have a function applied on a set, and I want to find the argument of that, so the argmax gives me the argument, right? So if I have a set, let's call this S1 up to SK, and I have a function from the set to the real values, then let's say that these are, make these concrete, 1, 2, 5, then the max S in the set S, right, for these values of S, right, this is going to be 5. If I have a function from 1, 2, and 5, and it maps it to a value 10, 20, and 5 again, then then the arg max over the set of the function is going to be equal to 2. It's the value 2 that maximizes the function. Oh, okay, yeah. So what is this function trying to do? So I'm writing down an optimization function, right? So this could be kind of, it's like the loss function that we've seen in regression or in, but now the loss function is defined so probabilistic. And I have parameters that I can choose. I can choose the means of the clusters, the cluster centers, and the covariances. Those are described, the means are all of the mu j, and the sigma j's are all the covariances. Those are the things I can change and optimize. And here is a function. This is a function that I want to make as large as possible. Okay, so the interpretation of this is that these are the set of points which are these are the Gaussians that fit the data very well. I want the data, each data point to be able to be assigned to one or more of the Gaussians and have a large likelihood. Right, so I want to if I do fix that these are all unit covariances, then and I only had one function, then I'm just basically fitting the best fitting Gaussian, and that all I can do is choose the mean, the center of that Gaussian, and that the mean, it gives me the maximum likelihood. And we had derived this early in the semester. But now we have other things we can do. We have multiple Gaussians we can do, and we can change also the covariance. Yes, yeah. So we're maximizing kind of the joint likelihood. It's not necessarily a probability, but it's proportional to a probability. It's a likelihood, and we're maximizing the likelihood not just for one point, but the product of all the points. And so if you do a log transform, it becomes the sum. Okay, great, yeah. So, okay, so let's get started. So let's get back into the lecture. So again, the goal was we're given a set of n points in RD, and we'd like to fit now some number k of these Gaussians, so that for each point we can define a likelihood that it came from one of those Gaussians or some mixture of them based on assignment probabilities. And we'd like to maximize that likelihood. We'd like to do this, the product of these, the max joint likelihood is the product of all the individual likelihoods. And so we end up with this formulation that we see here at the bottom. And you can do, more intuitively, you can do a negative log transform and get it to be a sum, right? A sum of these log likelihoods we want to minimize. And then you do an argmin instead. And this one should look a lot like the k-means clustering formulation. You're minimizing this negative log is going to look like a squared distance. So you're doing something like minimizing the sum of squared distances of the points, but you can do a couple of changes. You can choose the stretching of this distance, and you can do a soft assignment. All right, so that's what we want to do, and I'm going to adapt the algorithm. So this is going to be the EM. I'll just describe what that means: expectation maximization. The EM algorithm for the mixture of Gaussians. Okay, so let me just try and I'll just write down the algorithm, and then we'll kind of see how this goes. So I'm going to choose. I'm going to initialize. So I'm going to choose. So K. Choose K points, S as a subset of X. Okay, and then I'm going to, for all Sj is going to be equal to some Uj. Is going to be one of the centers. Okay, and then for all Xi in X, I'm going to, so just to initialize, I'm going to set Wi of X, Wij is going to be equal to 1 if phi of S Xi equals Sj. So otherwise, Wij is equal to 0. Okay, so I'm going to initialize with the hard clustering, and I can choose basically any sort of hard clustering I want to initialize with. Okay, and all the same things we said about initializing, k-means, clustering, basically the same thing is true here. Okay, so but I need to somehow initialize, and this gives me a clustering, but I don't have the soft assignments yet. Okay, but this will allow us to get some starting point, which we're then going to iterate on, like Lloyd's algorithm. Yeah. So otherwise is just like OW, so short for otherwise, which is takes a lot of space to write out. Yeah. Otherwise. Okay. If that's the handwriting's any better. Okay. So now we're going to do a repeat until, and so this repeat, we're going to, it's going to kind of have two steps again, the assignment step and the update step. These are going to be the maximization step and the expectation step in this EM framework. Okay, so the first part is going to say for j equals 1 to k, I have to kind of do the assignments, and the assignments then have to be these soft assignments. Okay, so we're going to start by calculating the total weight. Okay, W I is going to be the total weight. W J is going to be the total weight of all the points assigned to the cluster. This is kind of like the number of points assigned. This would be I equals 1 up to n of Wij. So this is the total weight of the jth of the clusters. Okay. Then I can set mu j, right? This is going to be the center, the best center of the cluster. And now this needs to take into account the weight. So I need to do a weighted average. So I'm going to do a weight over all xi and x divided by, now not the number, but the total weight. Okay, because each xi could be partially assigned onto this. So this is kind of an average over the total weight. So I'm going to do this. This is a weighted average of xi's. Okay, so it's kind of like an average, but it takes the weights into account. If a point has 0.5 into one of this cluster, it counts as half a point in the average. If it's 1 in the cluster, then it counts fully in the average, right? If it's 0, it doesn't count in the average. Okay, so this is just a weighted average for mu j. Okay, and now I also need to calculate the covariance as well. Yes. And so this again is going to be a weighted average. Okay, so again, Wj sum over xi in x of the weight. And now to compute the covariance, I have to basically it's going to look at the average deviation, average squared deviation from the mean, right? And this I can just write out in vector form as xi minus mu j transpose. No, not transpose. Xi minus mu j transpose, right? So this is an outer product. This is an outer product, and that's going to give me the covariance matrix. Each point adds a rank 1 component to it, and together this is exactly what the weighted covariance of this matrix is. It's the average squared deviation from this. So from the mean, this gives you this d by d matrix. Okay, so I can solve for it optimally. I don't need to optimize or anything. I've got this basically closed form solution for this, which is nice, just like I did for the mean. Okay, so this is how I solve for the best covariance of this. There's more variation along a certain direction from the mean. This is going to be larger in that direction because I have more differences from the mean mu j from more points. Okay, so this is how I update the optimal kind of clusters. They're defined by mu j and sigma j. These are going to define the j of the clusters. I do this for each of the clusters. Okay, and then so this is the maximization step. This is maximization, or the assignment. Then I need to do the other half of this is sorry, this is, I have this wrong. This is called the expectation step. It's the averaging. Expectation. This is the update. Okay, and then I need to say for each xi in x, right? Now I need to update the assignments, right? And so the assignments again, it's for each j in 1 up to k, right? So it's for all the clusters, I'm going to set wij is equal to fj of x. This is the shorthand where fj of x is equal to f of mu j sigma j of x. Okay, so just fj of x over the sum of j equals 1 up to k of fj of x. Okay, so this is exactly how I assign these weights, right? I update the partial assignments here. Okay, and I'm just going to do this. So basically until so converged. Okay, and how do I know when it's converged? I can look at the average change, the average rate of change, or I just run for some number of steps. Okay, they're, again, the kind of strange ways of determining is it converged or not, and the challenges with that are basically the same as before. This is known as the so maximization step, right? Or the so assignment. Okay. Okay, so this is the algorithm. It's not, so it's, you know, if you got Lloyd's algorithm for k-means clustering, it's not that much harder, right? You have to keep track of this other representation of the, instead of a full-on assignment, think of a partial assignment. So for every data point, I have to create these weights of the assignment, but I have a way of doing this. Once I can write down this Gaussian function, fj, I can just calculate these and kind of take the likelihood ratio of this versus the sum of all the likelihoods. Okay, and to calculate the most optimal kind of Gaussian for each of the Gaussians based on the assignments, well, I can, you know, I'm basically calculating the mean in the same way, but I have to update it with the weight. So it's the weighted mean. So it's not that much harder. I just have to take the weights into account. And I have to calculate the covariance as well. And that turns out it's not that much harder than calculating the mean. I can just write down the weighted sum of all of the outer products of the difference vectors. Okay, so this is the algorithm. And the advantage of this over Lloyd's algorithm and over k-means kind of clustering in general is that this gives you a more kind of a probabilistic interpretation of what's going on here, right? I'm saying I'm saying that the data came from some underlying sort of distribution. I'm assuming it came from these stretched Gaussian distributions, and I could generate data from this distribution if I wanted to, right? And this is kind of it's maximizing the underlying, so like the underlying likelihood under this model. So it's kind of a little bit more well formulated than the k-means formulation. Right, so if I look at an example like this, if I don't use the weighted formulation, okay, if I don't use the soft assignment, this is not going to quite converge to the right solution. What's going to happen is these points that are in the intersection of these two, they probably could be in either of these two clusters. What's going to happen is I'm going to somehow kind of split the difference in some way and say, well, some of these points are in mu3 and some are in mu4. What's going to happen is that mu3 will shift over here and mu4 will shift over here. It'll have less points down here in the bottom, or maybe one of these may have less points. It might have more points too, because it stole points from the other cluster. And so the centers are not going to wind up in the right spot, and it won't really converge to the right distribution. So I need to do this soft assignment for this to actually, you know, you can show will to actually converge to the right generating distribution when you get these non-trivial sort of kind of overlaps of the likelihoods. So that's why the partial assignment is going to be important here. All right, but it's not that much harder to deal with. Okay. All right, I guess I want to wrap up with two things. One, I want to tell you about this other sort of clustering so you get a sense of how diverse the type of clustering can be. That'll only take a few minutes. So I want to first talk a little bit about when should you use k-means clustering and Lloyd's algorithm, and when should you use mixture of Gaussians and this EM algorithm. So do people have thoughts? Is the EM algorithm, this mixture of Gaussians, always going to be better? Or is because it does something here with it's the modeling is better? Or, Lloyd's algorithm is what most people use. It's, it's easier. So maybe that makes it better. Yep.
It seems to me like, doing all of this stuff with your, sigma j, and all of these computations, it seems like this would be more computationally expensive.
Yeah. So if you look at the runtime of these, both of these are built into most libraries you want to use that have so scikit-learn has both of these built in. The runtime for this is going to be so slightly slower, especially in d dimensions. You have like a d squared step here, right? This outer product generates a d squared dimensional matrix, so that's going to make this a little bit a little bit slower, especially in very high dimensions. So, but it's not too much slower. It's the runtimes. It's, and I would say mixture of Gaussians might end up being about factoring in reading the data and starting up and then looking at the results, maybe like 10-20% slower. So it's going to be a little bit slower, but not typically not so much you're going to have to worry too much about it. There could be cases where it's going to be, factor 2 or 3 times slower, but you're going to spend a lot of time looking at the results afterwards. And if you factor that in, it probably doesn't make that big of a difference. Yeah. Yeah, so if you thought they were going to be disjoint from each other, and I don't need to worry about the overlap, then the k-means formulation is probably fine, and it's so simpler. If I thought that my clusters are not going to have any non-trivial covariance here, I'm not going to really need to stretch them out. I'd like things packed in the original distance. I don't want to do that. Then I don't want to worry about this, about also fitting the covariance matrix and possibly stretching things out, right? So if I think, on the other hand, if I think my data might look like this, where there is maybe some non-trivial kind of stretching, or I want to fit a probabilistic notion, then I might want to fit this mixture of Gaussians instead. I get a richer model. The other thing that has been mentioned is that to fit this, I have more parameters I have to fit. I not just have to fit the centers, but I have to fit the stretching, and that's like d squared parameters. That's a lot, can be a lot more parameters. So I should have a lot more data if I want to use this. If I have like 50 data points, I want to fit 4 clusters. Okay, k-means formulation that's probably reasonable. But if I have 50 data points and I want to fit this, that's kind of stretching what actually makes sense to do. I probably, for 4 clusters with covariances, I might want, in 1D that would probably be fine, but in 2 or in 10 dimensions, I'd probably want like at least 1,000 data points to really trust that I have really good, good clusters. The more dimensions I have, the more data points I would feel like I would need to have here. Whereas actually the k-means formulation, higher dimensions, it's actually fine. Like you're less concerned about that because you kind of the centers, there's a low dimension span that passes through them, and it only really cares about that. So they're kind of trade-offs based on how much data you have, how much modeling you want to do. If you assume you want to keep things kind of more circular, there are some trade-offs that you have to decide when you have these different sort of formulations here. Okay, I want to conclude with one other kind of clustering algorithm, mean shift clustering. Okay, this takes as input Okay, X in RD and a so kernel, which is going to be RD cross RD. It's a function, and typically we'll use so the Gaussian. So it's going to be X negative P minus Q squared, and there might be some some standard deviation. Typically not a covariance version of this. Okay, it does not have a parameter k, the number of clusters. You do not tell it the number of clusters. The only real parameter you have here, this is your only real parameter. This what the standard deviation of this. Okay. Okay, and what this is going to do is a sort of a weighted average. You're going to need this concept of, we'll call this mu p, which is going to be, let's say of a point p, xi in x, or, of k of xi p at xi divided by xi in x. Okay, so for a point P, you're going to kind of think about this Gaussian or this kernel as saying which points are close and which points are far. And you're going to have a bunch of these other sort of data points. And then we're going to take a weighted average of all of these data points. And the weighted average will move from P to mu of P. Mu of P will be a weighted average of all of the nearby points to P. So those orange points are nearby. We're weighted more if they're higher under this kernel. So the points closer to P are weighted more, and I'm taking a weighted average based on those points. Okay, so now the algorithm is just going to be repeat until something. So for all P in X, I want to so calculate this mu of P. Okay, this weighted average of the points in the neighborhood scaled by this kernel, and then for all P in X, okay, I'm going to set P, I'm going to move it to mu of P. Okay, and I'm going to do until so converged. Okay, so this is the algorithm. Okay, so what's happening here? Kind of weird, kind of different than before. Where are the clusters? Well, what's going to happen is all of the points that are nearby P, right, all the orange points, are all going to move to their weighted average too. I calculate them first and then I move them. Otherwise, it's kind of moving around in hard to understand way. But I calculate all of them. They're all going to move kind of towards the center of mass of the points nearby. They're all going to be kind of moving in. Okay, and they're going to all kind of verge to the same spot. And eventually all the points within some distance of each other, they're going to be in the same cluster. Okay, so you're going to get kind of, think of having a bunch of points here, 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 and after a number of steps, they're all going to kind of move into the same center, and I'm going to get these three groups of points all reassigned to the same spot. And that's how I'm going to find these clusters. So if I use the full Gaussian kernel, they'll eventually move to kind of all the same spot. But if I use a truncated kernel, at some point it will stop. Before then, and I'll, again, they won't be exactly the same, but up to some precision, they'll be the same. So this is a very different sort of approach than the other ones we talked about. And it'll work if, for instance, if the data is kind of trailing off here and I get these weird structures of the data, it will kind of pull it into where the center of mass is, even if I have these weird structures. But if there's too much mass there, it might clump together and stop. Okay, and it kind of does this in a weird pattern. So it's a very different algorithm, just to give you a sense that clustering is this vast space with a lot of different ideas beyond what we've talked about. All right, so we'll stop here, but I can so take some questions as well. Let me